Hello and welcome to lesson number 7 in the series The Introduction to Functions. This lesson is called Boundaries and Restrictions. Hi, my name is Dylan. By the end of this lesson, you should be able to analyze a function and calculate any values that are not valid for the function, and determine the domain and range of the function. In this lesson, we're going to see how everyday terms like restriction, limit, domain, and range are used in mathematics. Now, my saying the word restriction might bring the following into your mind. Some movies contain unsuitable scenes, and so they have a specific age restriction, meaning, for example, no under 18s are allowed to watch this. Some clubs and raves are arranged for a specific age group, and so there is also an age restriction in terms of who may attend. Of course, there are also health and safety regulations related to the sale of alcohol and cigarettes. For some functions, we may find that there are also restrictions in terms of the input or output values that are allowed. Take a look. In the previous lesson, we were working with the equation y is equal to 20x plus 100. Now, say for example, we know that x is equal to 2,5. That is our input value. It's very simple to find the output value by simply substituting that input value into our equation. So therefore, y will be equal to 20 multiplied by 2,5 plus 100. So therefore, y is equal to, well, I know that 20 times 2,5 is equal to 50. So y is equal to 50 plus 100, which is simply equal to 150. Well, that seemed quite logical. When the input is 2,5, the output is 150. But in any calculation, we need to make sure that our solution makes sense in that specific context. Now, what do I mean by context? Well, we need to go back to that specific situation. What was this formula describing? We considered a bank balance in terms of deposits that were made. In this case, we used discrete points. As x in this situation represents the number of deposits, does it make sense to let x be equal to 2,5? Think about it. We can go to the bank and make a deposit once, twice, or even 50 times. But it doesn't make sense to go 2.5 times. Even though this input value has been used correctly in an algebraic calculation, it is not admissible in this context where x represents the number of deposits. We need to determine the values that are admissible or allowed. In this case, the input values are whole numbers, and we can write that like this. X is an element of the set of whole numbers. Now, the whole numbers examples are 0 or 1 or 2 or even 1,000. Now, restrictions on the input values must clearly have an effect on the output values. In the case of the bank account and deposits being made, the total amount can never be 150 Rand because that particular input value is not allowed. Now remember, we are ignoring the effects of interest. In grade 10, you will look at many functions where there are restrictions on the input values in place. Think about drawing a semicircle, for example. First thing I've done is I've drawn my Cartesian plane, and I'm going to draw a semicircle with a radius of 8,5 centimeters. Remember that a semicircle is simply half a circle. Now, can you think of any restrictions that would apply in this context? Well, if I were to let the radius of my semicircle be 0, can you see that the semicircle would simply not exist? So whenever we are working with a semicircle, we always add a restriction on the radius. We write it like this. We say that the radius may not be equal to 0. Can you think of any other restrictions? Have you ever solved an equation and the answer just simply doesn't make sense? Think of finding the square root of a number. What if we need to find the value of x such that x squared is equal to -9? What input value can be squared so that the output value is -9? Well, this is not possible using the real number system. But if we were to work with the imaginary number system, then we would be able to find an answer. In the real number system, there are no input values that can be squared to give a negative output value. Now let's consider restrictions in the case of division. Here I have an expression. It is 3 divided by 1 minus x. And I know that the denominator, this expression at the bottom, may not be equal to 0. So does that mean that x may not be equal to 0? Well, let's check that out. If we allow x to be equal to 0, then the expression will become 3 divided by 1 minus 0, which is equal to 3 divided by 1. And this is defined. We have an answer for this. This is actually just equal to 3. So the denominator not being equal to 0 doesn't necessarily mean that x may not be equal to 0. Let's take a look at the case when x is equal to 1. If we now let x equal 1, then our expression becomes 3 divided by 1 minus 1, which is equal to 3 divided by 0. Aha, here we have a problem. 3 divided by 0 is not defined. So x may not be equal to 1. So can you see the difference between the whole expression in the denominator not being allowed to be equal to 0 and x not being allowed to be equal to 0? Our restriction is that x may not equal 1. We write that as follows. X may not be equal to 1, because when x is 1, then the entire expression in the denominator becomes 0. You may want to remember this by looking at these simple pictures. It makes sense for you to go through life upright with your head at the top. So you can think of it like this. If this were a fraction, 0 is allowed to be in the numerator. But it doesn't make sense for you to go through life upside down or with your head at the bottom. So again, if you were to think of this as a fraction, you may not have 0 in the denominator. So clearly for some functions, there are some input values that are simply not allowed. Now, you can take these ideas of restrictions to develop a notion of domain and range. And you can think of domain and range as a region or a location. So if you live in South Africa, then you obviously live in one of the 9 provinces. This map shows where Gauteng lies within South Africa, and it shows the boundaries of the province. Now, if you do live in Gauteng, then you cannot possibly live in Durban, because Durban doesn't lie within the boundaries or borders of Gauteng. And the same way, there are specific locations within Gauteng where you cannot live. For example, you cannot live in the middle of the Yokske River. You also cannot live down a mine shaft. Let's now define what we mean by domain. The domain of a function is all the values of the independent variable for which the function is defined. Remember that the independent variable is x. A casual way of thinking of this is as follows. For what input values does the function make sense? Because we deal with the set of real numbers or real values, in grade 10 we consider where the input values lie within the set of real numbers. In this example we looked at earlier, we saw that we were working with the whole numbers. In other words, we had already defined our domain as the set of whole numbers. Let's go back to the example when we saw restrictions imposed on the input values because of a denominator. In this expression, we can have any input value we like, that is positive or negative numbers, whole numbers or fractions. The only thing we are not allowed is for an input value of 1 to be inputted into this expression. So in other words, we state our domain as follows. the domain is the input values, where the input values are part of the set of real numbers or come from the set of real numbers, but the input value may not be equal to 1. When working with real numbers, we often use interval notation, which describes the location of the values by using the concepts to and from. We can describe South Africa as an example. The land in South Africa extends from the Atlantic Ocean in the west to the Indian Ocean in the east. In other words, South Africa lies between the Atlantic Ocean and the Indian Ocean. Look at this graph. The input values are the numbers from 0 to 7. We can represent the domain as follows. Look carefully at the notation that is used. Remember what you saw on the graph. Now focus on the input values shown in the next graph. How many input values are represented on the graph? The graph is a continuous line, and therefore it represents all the real numbers between -3 and 8. That is infinitely many numbers. -3 is excluded, while 8 is included. And as you know, it is impossible to represent all of the real numbers between any two values. So how are we going to represent the domain? Well, look carefully. We use a round bracket with the value -3, that is excluded. On the graph, the point on the line was marked with an open dot. X equal to 8 is included in the domain, so we use a square bracket. On the graph, the point was marked with a closed dot. So the domain describes where the input values live in the real number system. But what about the range? Can you guess what the range refers to? Well, as we already know, a function describes the relationship between the input values and the output values. So as we've seen in many equations, the output values, or y, depends on the value of the input value, or x. So let's define range. The range of a function is all the values of the dependent variable for which the function is defined. The range clearly depends on the domain. So let's have a look at some examples where we focus on the range. In this case, the range is discrete values. We can represent this range as follows. Note that for discrete values, we cannot use interval notation. Let's look at an example of a continuous function. The range includes -2, but excludes 5. Think about the notation that we will use to represent these restrictions. As the output value -2 is included, we use a square bracket. For the excluded value of 5, we use a round bracket. Remember that interval notation describes values from a maximum to a minimum, and so it includes all of the real values in between. Now here is an important note that I want you to pay special attention to. From now on, I would like you to make sure that all of the answers you get from solving an equation make sense in the context of that equation. You cannot simply automatically accept all of the answers that are generated. Make sure that they make sense in the context.